Hello and welcome to the third Launch and Learn webinar of the week. Today's Launch and Learn is going to be presented by Dr. Miriam Smith, Business Development Executive for Keller in North America. Dr. Smith's career spans over 20 years of geotechnical engineering practice and ground improvement design, build, construction. On today's presentation, she will be discuss the Rigid Inclusion Task Force of the Deep Foundations Institute Ground Improvement Committee. Before we start with Dr. Smith, don't forget to sign up to our YouTube channel and stay in touch with us all the time. So for now, Dr. Smith, the floor is yours.
Thank you. I'll tee this up. Can you see my presentation?
Yes.
All right. Well, thank you for this time to chat. I'm really happy to be here and chat with everybody. I know Christina already mentioned the title of the presentation. It's a little wordy, but I'll say it again. Today I'm going to discuss the recently published commentary by the Rigid Inclusion Task Force of the Deep Foundations Institute Ground Improvement Committee. Okay, there we go. All right, so I'm going to begin my presentation by briefly discussing the why behind the work that I'm going to discuss today. What was the need and what was the purpose? And who performed this work? It was made up of several experts across the country, in different time zones, with busy schedules. And then the bulk of my presentation is going to be the what. And I'm going to discuss the results of this work, and that's going to be the bulk of my presentation. But I really would like everyone to keep in mind the why and the who as I go through this, because those are equally important. Okay. So the why. Well, currently, we know thousands of structures are supported throughout the United States on the ground improvement technology we refer to as rigid inclusions. However, there currently exists no industry-wide standard for the selection, design, and verification of this ground improvement technology. And they're gaining momentum and they're gaining popularity, and they're installed on often complex sites with a lot of complex loading conditions in a lot of situations. And the purpose of this work was to provide valuable guidance to designers and reviewers and owners for the design and the verification of these systems. Okay, I'm having a little bit of technical issue here. So, who performed this work? And if you'll give me 1 minute, I need to do something here. I'm going to stop sharing my screen. Okay. 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 All right, are we back?
Yes.
So anyway. So the Rigid Inclusion Task Force of the DFI Ground Improvement consisted of consultants, academics, and design build contractors. And I'm really proud of all the work that this group performed. And so I want to give credit where credit is due. So I'm going to go through and name this task force one by one. We had Jerry Bishop with Kiewit Infrastructure, Jim Collin with the Collin Group, Aaron Gallant with the University of Maine, Marty Hudson with the Turner Construction Group, Larry Johnson with GZA, Ken Niss, a colleague of mine at Keller, Mike Pikowski with Helical Drilling, Tim Siegel with Dan Brown and Associates, and also the current chair of the DFI Ground Improvement Committee, myself, Sonia Swift with Menard USA, Sam Warren with Farrell Design Build, and Cord Wisman with GeoPeer. This group would also like to thank our colleagues at our respective companies, as well as the DFI group, because we are very thankful for all of the review, the peer review, and the comments that we received. This is truly a great collaborative effort, and I'm very proud of the work that this group performed. So what did this group deliver? Well, a large commentary for guidance for the design and the installation of rigid inclusions. And it's a lot of information, so we broke it up into 2 documents. The first one has been published over the summer of 2023, Part 1, the selection and design of rigid inclusions. And then Part 2, I was told this morning that it's going to be published next week. So I am only going to talk about the information in these documents today. I am not going to add any additional editorializing. And the figures in this presentation are the figures from these documents, but I'm also including a couple extra figures and photos from members of the task force. Okay, so the first important thing is to define what a rigid inclusion is. And generally, a rigid inclusion is a stiff, columnar, slender, vertical element. And it is distinguished from a deep foundation system by the fact that it is not connected to the foundation system. So it's generally separated from the foundation system by what we commonly refer to as the load transfer platform. Now, this load transfer platform is generally compacted aggregate, so you might see it have names like footing pad or aggregate cushion. It's got several names. It can range anywhere in thickness from 6 inches to several feet, but most commonly it's referred to as the load transfer platform. And it is an important component of the design of these systems. And together, the load transfer platform and the rigid inclusions comprise of a composite system that allow designers to develop design structures to bear on shallow foundation systems. So it's that disconnection from the foundation element or from the foundation system that distinguishes rigid inclusions from deep foundations. So what that means is a wide variety of materials can be considered rigid inclusions. Timber piles, steel pipe piles, steel H piles, grouted aggregate piers. As long as they're not connected to the foundation system, they are technically rigid inclusions. However, the focus of this work is primarily on what we commonly referred to as rigid inclusions, which encompasses unreinforced, cementitious, cast-in-place elements. And these are generally installed using proprietary methods. So the tooling and the technology, and even sometimes the design approach can vary a little bit. And we're going to discuss that briefly today. But just keep in mind that these are going to be focused on unreinforced, cementitious, cast-in-place elements. So let's talk a little bit about the load distribution to rigid inclusions. Again, like I mentioned, a load transfer platform is an integral part of the system design, and it's going to play a significant role in the load distribution to the rigid inclusions. And there's a couple of ways of evaluating that load distribution to the rigid inclusions. One could perform numerical analyses. There's several load distribution models that exist in the literature, or the designer may simply choose to assume that 100% of the load goes to the rigid inclusion. But generally, it's going to be some load sharing. We'll have some load going into the rigid inclusion and some load going into the soft soil in between the rigid inclusions. And the load distribution is going to look a little bit like this figure here on the right, where at some point, we're going to have a neutral axis. And this occurs where the rigid inclusion and the soil move together at the same rate. As when the rigid inclusion is equilibrium and it's moving at the same amount as the soil, there's only one location, and it's what we generally call the neutral plane. And above the neutral plane, we've got some down drag or negative skin friction. And below the neutral plane, then we're getting the resistance or the positive skin friction. And you can see that at the load at the top of the rigid inclusion in this typical load diagram, the load is going to be higher at the neutral plane. So in all cases, we want to evaluate both the structural capacity and the geotechnical resistance of these systems, the rigid inclusions. And you want to check both, and whichever controls will control the capacity of the rigid inclusion elements. So let's talk about these two just briefly. For the structural resistance, it is appropriate to use allowable stress design, and in accordance with the IBC Table 18. And these things will be brittle in flexure without reinforcement. Compressive strengths may vary from 2,500 to 4,500 psi. And we want to evaluate the structural resistance for the serviceability state. We want to consider that maximum load at the neutral plane when these are loaded in compression. And so that is an important check when you are evaluating rigid inclusions under compressive loads. Also, we want to evaluate the geotechnical resistance of these. And like very similar deep foundation elements, you can evaluate the geotechnical resistance by adding the shaft resistance plus the tip resistance. And it's important to note that the down drag loads do not exist at the ultimate condition. So essentially what happens is at the limiting state, your neutral plane moves up. And at the very limiting state, we are not taking into account those down drag loads. Factors of safety can vary anywhere from 1.5 to 2.5. That's going to be a function of the consequences of exceeding the factor of safety. So those are generally decided upon based on the use of the rigid inclusion, whether or not they're being used for settlement control versus bearing capacity, and of course the critical nature of the structure. So let's talk a little bit about settlement. It's not, again, going to be too dissimilar from evaluating pile groups. But again, the load transfer mechanisms are going to be a little bit different. So since we're not connected to the foundation system through a pile cab. And the total settlement is going to be equal to the compression of the load transfer platform, the elastic shortening of the rigid inclusion, and then the settlement below the rigid inclusions. And the elastic shortening of the rigid inclusion, we all know it's going to be PL over AE. So it's going to be very, very nominal. But we want to look at the settlement beneath the rigid inclusions, and we can consider this simplified settlement model that is shown here, where we have uniform load distribution down to the neutral plane, and then it's distributed at different angles below the neutral plane. Now, you can do numerical analyses. Good way to understand the total settlement of the systems. Those can often be cost prohibitive. So this is a simplified model that we present in the paper. So I know I said that rigid inclusions are generally not connected to the foundation. However, they have been known to be connected to the foundation. So it throws a little bit of a wrinkle into the definition. But there are times when we might reinforce these rigid inclusions. And one of those times would be to resist tension loads. And concrete and grout and tension should be limited according to the American Concrete Institute code, but don't get a lot of tensile resistance from concrete and grout. So most designers agree that the steel reinforcement should be designed to resist all the tensile load with the appropriate load factors. And you can evaluate the uplift resistance by adding the geotechnical side resistance and the weight of the rigid inclusion. And similar to a pile group, you can evaluate multiple rigid inclusions using those methods. Let's talk a little bit about rigid inclusions supporting structures. Again, these have been installed under structures throughout the United States They're gaining a lot of popularity. And generally in these cases, we are subjecting the rigid inclusions to compressive loads, but they might also be subjected to some lateral loading and tensile loading. So let's talk about the rigid inclusions beneath structures. So first of all, what's really important to note is that rigid inclusions do have the potential to affect the shear stresses in the bending moments in footings and slabs. So this is, again, where the LTP can become very important. And it's like with any ground improvement technology, you're not always counting on uniform support if you do have these hard points beneath your foundation systems. So it's something that must be communicated with the structural engineer if you are going to use these rigid inclusion systems beneath the foundations. And these stress concentrations, or these hard points, are dependent upon several factors. The applied stress, the thickness of the load transfer platform, the rigidity of the foundation, the spacing of the rigid inclusions, and again, the difference in stiffness between the rigid inclusion and the matrix soil. And I hope you can see this photo right here. It's a really good example of a hard point beneath a slab. You can see the cracking right above the rigid inclusion and the cracks emanating from that hard point. This was a case where rigid inclusions were installed and the LTP was neglected in design and installation, and this was the result on the slab. So it's very important to be mindful of both the design and the installation of LTP beneath the foundations and above these rigid inclusions. Let's talk about rigid inclusions subjected to lateral loads. And they may be subjected to lateral loads due to wind loading or even inertial loading during seismic events. And the first mechanism of resistance to lateral loads is going to be passive pressure behind the side of the footing. This is often reduced because we know you have to mobilize a lot of movement in order to maximize full passive pressure. So it's reduced to a certain extent. And the second mechanism is going to be base shear, both beneath the LTP, above the LTP, and above the rigid inclusions. And why this is important is because these lateral loads due to wind or inertial loading can impart lateral loads on the top of the rigid inclusions. And you want to evaluate the shear and bending or the structural integrity of these rigid inclusions in these situations. And these can be evaluated generally using some sort of conventional L-pile or group analysis. Now let's talk a little bit about rigid inclusions supporting embankments. Again, they are going to be subjected to compressive loads. And when I say embankments, I'd also like to lump in there MSC walls and tanks, because we're also going to have some different loading mechanisms now due to potential lateral deformations in the subsurface soils due to these systems. So now it's really important to evaluate the structural integrity of the rigid inclusions when they're subjected to these lateral deformations beneath these systems. I'll talk a little bit about that here. So generally, the lateral spreading and the geotechnical stability of these systems is governed by the area placement and the stress reduction on the soil, and it is not a function of the lateral capacity of the rigid inclusions. And rigid inclusions may be installed under these systems to transfer the loads from the embankment, the tank, the MSC wall, to a deeper, more competent layer, which thus takes some load off the soil that could be potential to fail or lateral spread. So we're reducing deformations by transferring loads to deeper soils, not via the structural capacity of the rigid inclusions. And this even includes if the rigid inclusions have some steel. And there are times when steel may be installed in the rigid inclusions under these systems, but it's not for the lateral capacity. It is more to maintain the axial capacity of the rigid inclusions if cracking occurs. However, the current practice is to prevent fracturing of the rigid inclusions. I think I skipped a slide. All right, so a couple of things to note. First of all, the lateral deformations in these systems cannot be predicted with two-dimensional limit equilibrium methods. Limit equilibrium methods may be used to evaluate the factor of safety, but not necessarily the deformations for lateral spreading. These rigid inclusions will generally fail in bending and not shear. So it's very, very important that any sort of limit equilibrium method does not count on the shear resistance or even the bending resistance of the rigid inclusions in these systems. And I know it's very common to use a composite strength approach for, say, aggregate piers, but it is not a valid approach for the systems on rigid inclusions because that doesn't really capture how these systems are going to fail. They're going to fail generally in bending and some cracking, and it's going to be a progressive failure. So the composite strength approach is not valid. So I also wanted to highlight some of the work that Dr. Gallant and his PhD candidates are doing at the University of Maine. There's a lot of great work coming out of those folks about looking rigid inclusions under embankments and global stability. So look them up as well. So again, we may perform two-dimensional limit equilibrium methods to evaluate the factor of safety. And generally what's recommended is that a reduced unit weight of the fill is used in the limit equilibrium method to account for the fact that the bulk of the load is transferred to a deeper strata. And that will give us a general idea of some factors of safety, but it will not give us an idea of the structural capacity of the rigid inclusions. So again, a two-dimensional or three-dimensional numerical analysis always gives us the greatest insight. It's not always economically feasible. So we are proposing a simplified approach in which a two-dimensional numerical analysis performed using this reduced unit weight approach. And we pull out of that numerical model the deformations. And then those deformations are imposed on the rigid inclusion in a conventional PY analysis, say like L-pile. And that's going to give us an evaluation of the structural integrity of the rigid inclusions. Not too dissimilar are rigid inclusions that could be subjected to seismic events. So currently there is a lack of consensus for the seismic design of rigid inclusions, but it has been widely accepted that in these events, the rigid inclusions will fail in both shear and flexural deformation modes. So it is not accurate now to only assume that they fail in shear. And we already talked about the inertial loading, but these things can be subjected also to kinematic loading, whether it's vertically propagating shear waves or ground deformations due to liquefaction or cyclic softening. And sometimes these ground deformations can be significant enough that a cracking in the rigid inclusion can result in dramatic reduction in bending stiffness. So again, we want to evaluate the structural integrity of these rigid inclusions if they are used in these environments. And not too dissimilar to the embankment approach, we would look at these by decoupling the displacements and the structural response. I'm sorry, well, decoupling the seismic numerical analysis and the structural response of the rigid inclusion. So the first step in the simplified decoupled approach is to evaluate the free field soil displacements by a numerical analysis. And then again, pulling out those deformations and imposing them on a rigid inclusion in a conventional PY analysis like L-pile. And again, 3D numerical analyses are ideal. They can be cost prohibitive, but where the projects can support it, that's where you're going to see the most insight. Let's move on now a little bit to the construction and the verification of these systems. This is a sentence right out of the paper, but I do want to emphasize that a high degree of skill and care are required to install rigid inclusion successfully. And most of these methods are installed using proprietary methods. And it's very important that the project team works together to design and understand the construction and the verification of these systems, because there's some construction risks such as cost, schedule, and even more importantly, system performance if a thoughtful planning process and robust QA/QC are not employed. So let's talk a little bit about that. So it's not uncommon for an indicator program to be employed prior to production. And during both indicator program and during production, the installer is going to measure several installation parameters, which include, but are not limited to, the crowd pressure, the rotary head pressure or torque, or driving energy or moment, the drill speed, both during initial penetration and withdrawal, the volume of grout take or concrete placed per interval, and the grout or air pressure, and most importantly, the installation lengths and cutoff depths. So these pictures are a little bit scary. This is a risk that you primarily see in sites with deep, soft organics or soft clays. And this figure that we have on the left, some broken rigid inclusions, and this figure that we have on the right, some grout heave. And the figure on the left is most likely due to ground heave. So in these soil conditions, when one rigid inclusion is installed, it can heave the ground adjacent to already installed rigid inclusions and break the ones that are already installed. That's one risk. Another risk is this grout heave. And it's not uncommon to get a little bit of grout heave as the soils reach equilibrium and some grout comes out. But if you start to see a lot of grout heave, that means that there are some issues with perhaps necking or disturbance. Now, these are being more widely addressed in the industry. So now most installers generally know how to address these concerns. And they may address these concerns by adjusting the grout mix, adjusting the sequencing and layout, or even sometimes adding a central steel bar just to hold things in place during installation. So a single load test on an installed rigid inclusion is generally a minimum standard. And this is done in accordance with ASTM D1143. I think we're all very familiar with this load test. But this is going to allow the installer and the designer to verify the assumptions in the design, as well as to verify the criteria that was established during the indicator program. Now, it's going to be a little bit different than loading a pile. Sometimes these things are loaded to geotechnical failure or failure in general. That is not as common. They may be loaded to 150 to 200% of the design load, or going back to our load diagram of the neutral plane, they may be loaded to account for the maximum load at the neutral plane. But again, the load testing program is something that the geotechnical engineer and the installer should work together to arrive at a suitable loading sequence. There are some times when we also want to evaluate the performance of the load transfer platform, because that ASTM D1143, that only will test the rigid inclusion element itself. So you may want to evaluate what happens in the LTP. And this is a picture here up on the upper left. There's this single rigid inclusion element. The LTP is being constructed. A cap is being installed on the system, and then that LTP and single rigid inclusion are being installed in order to evaluate the system that works together. Again, those only test one element. And it's generally a good way to, or it's generally the minimum standard of practice, but there are some cases where you might want to evaluate a group of rigid inclusions. Say you've got some very, very soft soils at the ground surface, or you're looking at a largely loaded area. However, these are not always going to be economical for mid to high rise projects. This is going to be, sometimes it can be very cost prohibitive, but it's not uncommon if you do need to look at the overall system to perform a footing load test that takes into account several rigid inclusions as well as the load transfer platform on top of it. And pressure plates and strain gauges can be installed to give you a good understanding of the load sharing between the soil and the rigid inclusions. Another important component is the cutoffs of these rigid inclusions. It's standard of practice to lower the grout or cut the top of the rigid inclusion elements to the design elevations prior to full curing. And you generally want to cut them down at the working pad or foot or more to protect them from damage. And most of the installers have different means and methods for performing this work, but it is very critical that even after this work is performed, that care is not taken to damage the elements with traffic, equipment operation, and the LTP placement. And generally, I have been told that I should emphasize the LTP placement. And it goes back to that slab photo I showed you earlier with the crack because the LTP was missing. Oftentimes, the LTP is installed by others than the installers. So again, it's very important to note that that is an important part of the design, and it does require its own inspection, QA, QC, and attention to the work. So I just wanted to highlight that as well. And I am almost running out of time. This has been a very quick overview. But one of the things I do want to point out is if you download these papers, there's a great list of references. Great papers to have in your library. And finally, again, I want to thank all of my colleagues on this task force. This probably has been one of my most enjoyable publications because we had these 12 folks get together collaboratively and actually produce these two documents. And I think it's a great contribution to the industry. And that is the conclusion of my quick talk. Are there any questions?
So we do have a few, actually. I'm going to go ahead and ask one, and then we'll get to a couple from our audience.
All right.
You want to unshare your presentation and we'll go split screen? Perfect.
I think I did.
The first one I want to ask is actually a process question for you guys doing this. What were some of the earlier guidance documents that you considered as you went through this? You mentioned ACI 318, and I think you mentioned IBC Chapter 18 as well. Was there anything else you guys looked really seriously at as a model here?
Well, we looked at all of them. And again, that goes back to our long list of references. And again, it goes back to the fact that there currently existed no industry-wide guidance. So every expert brought to the table the list of references that they felt needed to be included, and we combined all that work together.
And what do you guys see? I know you said you weren't going to editorialize. I don't know if this crosses the line or not. What do you see as the next steps here? Is this just done? You guys are going to drop this document, or is there going to be some kind of follow-up activity?
Well, I know that ASCE has a committee right now that's also looking at some similar work on rigid inclusions. And I know ADSC has been looking at performing also some work on publishing some documents on rigid inclusions. And it's our goal, our hope to get all of these experts from all three committees in one room and to at least have a discussion, because there are still some unknowns, and there are some things that still have not been widely agreed upon. So I think the next step would be to bring all of these committees together, all these experts together, have a round table, because I know those other two committees are also moving forward.
Perfect. Good answer. That's what I was fishing for. So you nailed it. So let's get a couple
you didn't
from
give me warning for that either.
Let's get a couple from the audience too. The first one came in from Amin G. Do we consider the settlement coming from the soft soil below LTP to calculate the total settlement of the system?
So I assume that they're talking about the soft soil in between the rigid inclusions. And
this is the beautiful thing about YouTube. You just got to go.
Yes, I mean, it's part of the load distribution model. So, you know, the settlement of the soil in between the rigid inclusions will impart some down drag on the rigid inclusion, so that influences the load distribution. And so that will influence what the load that's transferred to the rigid inclusions, and then how the rigid inclusions transfer that load. So it is included in that approach.
Okay. Another one from the audience. Is there any guidance for the load distribution sharing between the rigid inclusion and the surrounding soil based on rigid inclusion diameter or spacing and the LTP?
Well, yes, there are a lot of load distribution models in the literature. So I would encourage folks to go to the papers and look at the references. But there are a lot of load distribution models that exist for evaluating how the load is transferred from the LTP to the soil and to the rigid inclusions. And, you know, always a numerical analysis too can shed a lot of light on that.
Okay. And I've got one more here. Was there anything as you guys moved through this that you intentionally had to leave out, that you just couldn't touch as part of this process?
No, and that's one of the things that that makes me very proud about these documents is I would say a lot of time was discussed on defining them, and then a lot of time was spent on deciding amongst the group how much information we wanted to give, you know, prescriptive versus guidance. And I think at the end of the day, we all came to the agreement that the level of guidance that we provided was very appropriate and very helpful. I hope everyone else sees it.
So what we're going to do here, I think we're going to wrap up with that. We did have a Keller promotional video we were going to play as part of this. After I sign off, we're going to try it one more time. So I don't know how threatening I can be. Hang around and watch the video, all you viewers out there. We tried it at the beginning and we had some technical issues and it didn't happen. Before we sign off, I want to say thanks to the viewers, especially those who submitted their questions and answered the polls we had in the chat. We really appreciate it. Without your participation, these events are not as valuable. So that is great. Thank you very much. Miriam, thank you for the presentation. That was really good. We always give you a fake time so that you can run over a little bit. So don't worry too much about it. And again, for all of our viewers, this was the third and final Lunch and Learn live stream we have this week. There are still sessions tomorrow. If you want to register, you can head over to the Geo-Institute website and sign up for those if you are so inclined. We hope you are so inclined. We have 2 live streams coming up next week to end 2023 for our YouTube lives. Geostrata Extra is next Tuesday. It'll be with Jean Benoit from the University of New Hampshire on measurement while drilling. And then next Thursday, you can join us for the third in a series of 4 sneak previews for Geo-Congress 2024. Next Thursday's presentation will be from Monique Anderson from Shannon and Wilson in Seattle on the Alaska Wave Viaduct project. And you can get more information about those at our Eventbrite page, and we hope to see you there for those as well. So thanks again, Miriam. This was fantastic today. I hope everybody out there enjoyed it. You stuck around till the end, so you probably did. Click like, subscribe, get notifications, and we'll let you know every time we post something to the YouTube channel. Sean Herpelsheimer was our producer today. Great job, everybody, and we will see you very soon.
Thank you.
work.